opportunity to share with you some experience in the field of the energy efficient buildings and indoor environmental quality. So I would like to start with some little bit more general issues or general questions, because we are now in the field that we are trying to reduce energy consumption, we are trying to minimize energy use in the buildings to save our atmosphere. So maybe just first couple slides will be on the topic, which is of course in background of all of that. So we know, and we can accept it as a scientific result already, that there is something happens in our atmosphere, that the temperature is rising and we are living in this period. Of course, that those pictures are very nice for the climatologists who are now at a meeting in Paris and they are solving the problems. How does it work? For us as a technicians, I think it's better to translate this picture into a picture which is more familiar for us. And it's a picture showing the development of the number of cooling and heating degree days. This is for the Northern Hemisphere. If you will convert it, I did it for the Czech Republic, where I'm coming from. And the situation was very similar. You can find even small decrease of the heating degree days. Of course, there is a question if this situation is created by us, or if it is the perpetual operation, or if it is the operation of our planet. If you see the diagram which I showed before and this one, you can find that in this scale of 450,000 years, which is very long, the temperature of our planet is posing like a human heart, and now we are somewhere here in this point. If we will skip to the larger scale and we will increase the scale of this diagram, so this is the situation in recent 10,000 years, and this is our civilization, starting with let's say the first societies with pyramids, and nowadays is the Industrial Revolution. So of course it's a question, and it's a nice question to discuss about it, if it is what happens in the atmosphere our task, our responsibility as humans, or if it is normal operation of this planet. But what is important, that decision of our politicians, of people who are deciding where to use money for funding of development, are decided, and they are decided that it's our responsibility, and we can find some measures based on the European policy, which I think we all are already familiar, that 2020 is the target to reduce energy, to reduce greenhouse gas levels, to increase the renewables. But because this target is approaching very fast, we are now in the 2015 and we are heading to this target very fast, it's necessary to have also some view what will be behind 2020. So the European politicians decided that the way which was started in these three directions, that means greenhouse gas levels, energy consumption and renewables in energy mix, is the right way. So the next target is 2030, where is another question or another demand to increase the greenhouse gas levels, to decrease energy consumption another 7%, and to increase the renewables in energy mix. Nothing more that this diagram means and shows that the way of reduction of energy needs, and this way is that which we will continue also in future. Of course, this is very nice. It's perfect, we will save our planet. But the problem is that the buildings which we are building, which we are designing, are built to create indoor environment. We are not creating buildings to save energy. We are creating and we are designing buildings to create environment where we can live, where we can work, where we can do what we need to do. If you look at the statistics, our kind of the civilization, our kind of the way of life is very, very related to the indoor environment. So while in outside environment, which is affected basically by the atmosphere, we stay about 10% of our life. Inside of buildings, we stay 90% of our life. And now try to remember and try to look into the newspaper in last couple of weeks. How many times did you read something about the quality of indoor environment? How many times did you read about the quality of the atmosphere and those general topics? So I think it's us task and it's us responsibility to focus on the topics related to the indoor environment of the buildings. Of course, we know that the indoor environmental quality has effect to different parts of our life. So first of all, we should take care about our health, but typically those issues are covered by some health laws, health regulations, so it's somehow solved, as I feel. Of course, there are studies related to the quality of indoor environment and productivity. This is a little bit softer measure and softer evaluation assessment of the indoor environment, but still the studies which are available are significant, and they tell us if you create a bad indoor environment, the productivity of people who are inside is not so good. Of course, the question is, how is it with residential environment, with homes? We are not working there, so why to create some special environment there, why to take care about it? But of course, it's the question of the comfort. And it's possible to find again the links between the quality of your residential environment and your next day output in your work. I think that all of us can very easily remember a situation when you don't sleep well, next day you are not in good condition to work. Of course, that now we are getting to the topic which is for technicians and for us a little bit difficult to describe, because we are able to measure the kilowatt hours and gigajoules of energy and all those things, but it's difficult to measure the quality of indoor environment because it's difficult to describe it. It's a state of the meaning. It's not measured, or it's not possible to measure it. We just think and we just expect that we have some tools how to describe in the physical way environment to get people into the quality of into the feeling of the comfort. One of the theories which is in background of that is the theory which says we have the source of the agencies, we have the transmission field, we have exposed body. So we can adopt this model to different parts of the constituent components of indoor environment, like for heat. So we have a source of the heat, we have a transmission field like air and radiation, and exposed body is typically human who is in the end of this. If you implement this model to the general and the complex view on the indoor environmental quality, we can see that the indoor environment is not only heat, of course, it's not only thermal comfort, it's of course air quality related to gases, aerosols, microorganisms, is the acoustics, is the lighting, all electrostatic, magnetic, ionizing and radiation fields which we are not able to see, which we are not able to feel, but it somehow affects us in the place where we are. And of course it's a psychological comfort. So all those parts and all those components of indoor environment creating our feeling if we feel comfortable or not. If we go further, and we will go to the energy which we need in the buildings and which we use in the buildings for creating the comfortable environment, we can go to Directive 2010-31, which is well known, which finally, or which create some kind of the definition, what is it, energy performance of the building. But what is important, that this definition is affecting and covers all main energy needs of the building. That means energy need for heating, for cooling, for maintaining of the air quality, for artificial lighting, and for hot water generation. And now if we will merge those two fields, that means the indoor environment and the energy saving and energy in the buildings, we can find that each measure which we do in the field of the energy savings has a deep impact to different parts of the indoor environmental quality. I would not like to make, because the presentation and this is not the lecture for our students, of course, so I would like to share with you one experience with a recently refurbished office building which has been refurbished according to up-to-date standards with high professional design office, with high professional company who did it, and the result is how you will see. So the case study which I would like to show you is about the heating of the refurbished low-energy office buildings. So the building has been built in 1965. It's a 14-floor office building with the lightweight facade. And during this refurbishment, the lightweight facade was replaced by a new one with very good performance. The U value, the overall average U value, including windows, opening and all of that, was designed that as 0.87 for north-east facade, and for south facade it was 0.68. Maybe you are curious now why it is better in south than north. The difference is because in the south facade were used better windows in terms of the solar radiation and solar transmission. This building has been equipped with the very, let's say, efficient outside louvers with both manual and automatic operation. And ventilation of this building, before it was a natural ventilated office buildings, because the offices are for 2 or 3 persons, 1 up to 3 persons, not big offices, and based on the standard regulations, it's possible to use or to design such building without mechanical ventilation of the offices. So it remains there, and it was expected that people who will stay there and who will use this building will open the windows and will maintain the infiltration rate about 0.3 hours, the 3 air change per hour. During this refurbishment was refurbished also the heating system. The old one, which was a very old-fashioned one, it was a one-pipe system with zonal control on the bottom of in the boiler plant, was replaced by, let's say, up-to-date 2-pipe system with individual control of each heat emitter. Because the heat emitters in this building are covered by some parapet, the heads of the control are on the capillary, and they are operating with each radiator. What was interesting that the horizontal 2-pipe system, heating system, which you can see here, which was in the floors, in each floor we have this type. By the way, it was relatively smart solution from the viewpoint of the aeration of the system, so the upper distribution network. So according to existing standards, if you design a heating system in the heated place, you do not insulate those kind of the horizontal pipings, because it's according to EN standard, it is something that contributes to the heating of the room, so it's not necessary to make a thermal insulation of this piping, so it hasn't been done. Control of the system was 2 levels, so one level was the equitherm control, and then the thermostatic valves on each radiator. The system was very well balanced. The equitherm curve, which you can see here, was running because it's based on the measurement on the real building, so this is the theoretical value, and here you can see the measurements. If you go further, and if you start to think what happens is that in such building and in such room, you have some kind of the internal gates. We have there 1 person in typical room, production about 100 watts, 65 cents in the very low level. We have a computer, LCD monitors, printer, and some kind of the fluorescent tubes. And we have in total, we have about 700 watts of the permanent heat load, which is inside of this room. Reason why we started to study it was that during the first heating period, the temperature in this building was all the time too high. So even the whole heat emitters were closed. There was no active thermostatic valves, all were all the time closed. The temperature in the room was in average 23.8, comparing to design temperature 22 degrees. And this lower temperature was achieved just by opening of the windows for cooling of this space. So we made some kind of the analysis, that means to put together the heat losses with the heat gains, so make very simple model, and the result of this model was this one, where you can see that the design heat load for heating output of the heat emitter in this room is 735 watts. But from that 735 in that design outside minus 12 temperature, we have about 500 watts permanently covered by heat gains in the room. And only this small part, this red one, is that one which should be delivered by heat emitter. Based on this small study and simple model, it's not scientific model, it's very simple model, we found that up to temperature about 0, outside temperature, is not necessary to heat the room. And if we are above 0, here is the overheating, and here is the reason of the overheating of the room. Second question which we had was, how is it with the infiltration? How is it with air change rate? So expected is 0.3 air change per hours. So we did a measurement, and the result was that it's 0.08 up to 0.15 air change per hour. So again, this is very alarming, because it doesn't work, it doesn't fulfill any requirements for the indoor environment quality, because there is simply not enough air for people. You can open the window, but at the moment the temperature drops down, and it's not an environment where you can feel comfortable. So next step was to create some kind of the monitoring what happens there, and try to play a little bit and try to do something with this building. So there was set up the monitoring equipment, and these diagrams, which are a little bit too small, but I think I just would like to explain you that this first period was as it was designed. So here you see the curve of the supply and return temperature in the system. So it's according to equiterm curve. This is that one. Here is the temperature on supply and return on the heat emitter. That means it's here. So during the whole January, there was no time, no moment when the heat emitter will switch on. So even the outside temperatures were minus 10, minus very, very low temperatures. So after that, the first change was that we decided to change or to add the thermal insulation on the piping, on the horizontal piping, to reduce that internal heat gains from the piping, which are uncontrollable, which just increase the temperature of the room, and which are creating that. So after this and after change of the equiterm curve, the result was again not successful. So the final measure which has been done was to reduce the equiterm curve. So after all those, the equiterm curve is fixed on the temperature 37 degrees. So from design temperature, which was 60 to 50, we get to the permanent constant temperature of the water in the system. At that moment, you can find some moments when the heat emitters are starting to work, but unfortunately still the temperature in the room is too high. So this was the result of the last heating season. Another measure is the installation of ventilation system, which will increase the air change rate, because the quality of air was not sufficient. So how to conclude is that if you make some change in the heating, it's not only the question of the energy, it's a question of the thermal comfort, of course, it's a question of acoustics, because at the moment you create the very high pressure losses on the thermostatic valves, you create the sound effects of that. It's of course a question of the psychology, because if you make something like that, the people who are working in that place are all the time or overheated, because they have closed windows and the heat temperature is too high, or they open the window and they are not working in the comfort because the cold wind is coming inside. So just to conclude, this is the picture which we should have in our minds anytime we make any change and any measure in the buildings. And I think the main issue and main conclusion is that we are not creating buildings for energy savings, but we are creating buildings for us, for the humans to live. Thank you very much for your attention.